In this video we're going to be looking at one and two tail tests, and then later on in the video we're going to be testing a one tail test on a binomial distribution. So when testing a null hypothesis, we also have to set up an alternative hypothesis, and this alternative hypothesis will indicate whether the test is a one-tailed test or a two-tailed test. And you can see I've got written here a one-tailed test looks for whether a parameter should be increased or decreased. So, for example, if we're testing a biased coin that we believe to be weighted towards tails, our null hypothesis is that the probability of getting tails is 0.5. We would write that like this. But we would say that the alternative hypothesis is that the probability is greater than 0.5. So in that instance, we would say that H1, the alternative hypothesis, is that the probability of getting tails is greater than 0.5. Now, we don't know what the probability of getting tails is going to be, but what we can say is that it's greater than 0.5, so our original hypothesis, the null hypothesis that the coin is fair, is not correct. We can also have the alternative hypothesis as a decrease, so this would be a lower tail test because it's less than our null hypothesis. So this is an upper tail test, the original problem, and this is a lower tail test. Now, a one-tailed test has a single part to the critical region. Let's say our significance level is 5%. Then for the lower tail test, it will be results that fall in this region. And we can show this like this. So for a lower tail test, if these are all the possible outcomes, 5% of the outcomes are at this end and the rest are above that. If anything falls into this 5% here, then it falls into the critical region, and that's when we reject HO. And it's the same for an upper tail test. However, where the critical region is different. So for our upper tail test, critical region is on the upper side, and so if anything falls into this 5%, then we would reject the null hypotheses. Moving on to a two-tailed test. A two-tailed test is when a hypothesis test is of the form that the null hypothesis is that the probability is not equal to a certain value. Let's call that theta. Let's just draw that one again. There's theta. So therefore, the alternative could be an increase or a decrease. So therefore, there's going to be two parts to the critical region. The critical region is going to be split into two pieces. So if there's a 5% significance level, if these are all of our probabilities, we're going to be looking at two ends of the scale. And that 5% is going to be split into two parts, so 2.5% and 2.5%. So we would reject anything that falls into this lower tail or into this upper tail. Now, it's quite difficult to conceptualize all of this without looking at an example, so let's move on to testing the proportion P of a binomial distribution. We'll do this, and I'm going to show you the method of how these questions should be written out, and that's how you're expected to write out these tests. So, reading the question, the sports scientists developed a drug that they claim makes full recoveries from a broken bone in under 4 weeks. The probability of this happening normally is 0.4. In a test, 13 out of 20 patients recovered in under 4 weeks. They claim that their drug makes an impact on recovery times. Test at 5% significance level as to whether their claim is true. Right, so our first step is to define the random variable and identify the parameter of the test. So our random variable here we're going to call x, and that's the number of people who were cured in under 4 weeks. So I've defined the random variable. We also need to identify the parameter of the test, and we do this when we state the distribution. So we say that X has a binomial distribution. Here there are 20 patients, so n is 20, but the probability is being disputed, so that we would write as P. Now we need to move to the second step, where we write a null and alternative hypothesis. So the null hypothesis is just what normally happens, so that's when the probability is 0.4. The alternative hypothesis is what's being claimed, so that's that the probability is greater than 0.4. So we can see it's a one-tail test and it's an upper tail test because it's greater than the original probability. We now also need to state our significance level, which has been given here, 5% significance level, and remember we write that as alpha. So alpha is 5%, which is 0.05. And very importantly now, we also need to state under what conditions we will reject HO. So we're going to reject HO if the probability of X greater than or equal to X is less than or equal to the significance level, which is 0.05. Now, just to help you remember how to write these, this inequality sign follows this inequality sign here. It's slightly different if you have a two-tailed test, because you have to do both types of inequality. And in a later video, we'll be looking at an example just like that. So now we need to carry out the test by finding the probabilities. So under HO, which is our null hypothesis, X has a binomial distribution of 20 and a probability of 0.4. That's what our null hypothesis states. And we're now going to test the information that they've given us using the null hypothesis. So we need to find the probability that X is greater than or equal to X, which in this case is 13. That was our observed value. 13 people were cured in under 4 weeks. And we need to test whether this is less than, the probability of this happening is less than 0.05. So can you see that this inequality here is mirroring what we said would happen if we reject HO. So finding the probability that X is greater than or equal to 13 is the same as 1 minus the probability that X is less than or equal to 12. And because now we have a less than or equal to probability, we can use the tables, and reading that off from the tables, it's 0.9790. And that gives us a probability of 0.0210. And we can see that this probability, 0.0210, is less than 0.05. It's less than the significance level. So we found our probability, and now we need to state our conclusion, the final part. So with this, we can see that the result is significant. We have enough evidence to reject HO, and there is evidence to suggest that the sports scientist's claim is correct. When we are stating our conclusion, it's really important to bring the context of the problem into your conclusion. So we're bringing the problem back to what they asked, whether their claim is true or not. We've said that there's enough evidence to suggest that the claim is actually correct. Now, I want to do just one more extra scenario where the claim is found to not be correct, and what that looks like and how we judge that. So I've added an extra scenario, and it's using the same information as above, but it states that an independent body tested the drug and 25 out of 50 recovered in under 4 weeks. Test whether their claim is still correct at the 5% significance level. So we need to go through all the same steps as we did before. So we need to define our random variable. So I'm going to say that y is the number of people cured in 50 tests. And we also need to state the distribution of y and identify the parameter that we're testing. So again, we're still testing the probability. So y has a binomial distribution, this time 50, because there are 50 different scenarios, different tests, and the probability is p. We need to state our null and alternative hypothesis, so they're going to be the same. HO is that the probability is 0.4, and the alternative hypothesis is that the probability is greater than 0.4. Our significance level is still 0.05, and we will be rejecting HO if the probability of x greater than or equal to x is less than or equal to 0.05. So now we need to find the probabilities and carry out the test. So under HO, y has a binomial distribution of 50 and a probability of 0.4, and we're finding the probability that y is greater than or equal to 25, because 25 is the number of observed values in this case, and we are mirroring the inequality throughout. So the alternative hypothesis here is greater than. That's what we would use if we're going to reject HO, and so we have to use the cumulative probability here as well. So that is the same as 1 minus the probability of x less than or equal to 24, which is 1 minus 0.9022, which gives us a probability of 0.0978. Now, from this test, we can see that getting 25 people to recover in under 4 weeks, 25 or above, happens 9.78% of the time, which is bigger than our significance level. So, in this case, the result is not significant. We can say that there is insufficient evidence to reject HO, and this test shows that the sports scientist's claim is not correct. In the next video, we're going to be looking at testing lambda in a Poisson distribution, and we'll also be looking at what a two-tailed test looks like.